Hi guys, welcome back to Data Every Day. Today we are looking at a data set of houses in Delhi, and we're going to try to predict the price of a house based on a bunch of features. So let's hop into the notebook. We're going to use NumPy and pandas for working with the data. We will use the train test split function and standard scalar from sklearn for pre-processing. And we'll use a whole bunch of models today. We have 3 different linear regression models, k-nearest neighbors, neural network, 2 support vector machines, one with a linear kernel, one with a nonlinear kernel, decision tree, and then we have a bunch of ensemble methods, random forest, gradient boosting, and then 3 more gradient boosting, but they're 3 different kinds: XGBoost, light gradient boosting machine, and cat boost. So let's go ahead and import that, and we can load in the data using pandas.readcsv. And we can grab the file path over here for the CSV file, paste that in, and take a look. Alright, and well, the first thing that I noticed now is we have a missing value in the target column, which means we'll have to drop that. So I'm wondering how many missing values we have here. We can get a better understanding of the data with data.info. And we can see missing values here, here, and here. So 4 different missing value columns and 5 object columns, which we are going to have to encode in some way. So let's start pre-processing. I'm going to, as usual, create a function called preprocessInputs. That's going to take in a data frame. It's going to make a copy of the data frame, and then it will return the data frame. So right now it's just making a copy, but we'll store the processed version of our data in X. So we pass in data, get back X, and now we can modify this copy. Alright, so I guess the first thing is to drop those missing value rows in the target column. So if we take the isNA matrix of X, this will be a true wherever there's a missing value. We can then sum across all the rows to get a total number of trues in each column. So we can see how many missing values we have in each column this way. And we do have quite a few in the target column. So these up here, we can definitely fill those in with some either the mean or the mode, depending on the column. But this one we do have to drop the rows because it doesn't make sense to try to predict values that you've already imputed. So let's do this. I'm going to get the indices of the missing value rows like this. I'm going to take the per square foot column, which is the name of the target column, take the isNA matrix like I did before, and that will return. Yeah, I'll show you what that looks like. If we just do this for the per square foot column, we'll have a true and a false wherever there's a missing value. So a true means missing value. And we can use this true-false series as an indexer for the whole data set. So like this. To be more precise, we'll use the .loc, using this as the row indexer and targeting all columns. And so that will be all the rows, the portion of the whole data set that has missing values in the per square foot column. We can then get the indices for these rows with .index. And now these I'm going to use to drop the rows. So let's take this and put it up here. I'll just change X to DF. And then I'm going to call this missing target rows. Then all I have to do is say df equals df.drop missing target rows from axis 0, which is the row axis. And anytime we're dropping rows, if we want to keep the indices in ascending order or consecutive values, then we want to reset the index afterwards. And we'll include drop equals true to avoid the old, to prevent the old indices from becoming a new column. Alright, so let me just comment that. Drop rows with missing target values. And then we'll actually fill the other missing values. So let's take a look at this. Let's do this. Okay, wait. Let's return this, get x back, and then take a look at this. So we have no more missing values in the per square foot column. We do have fewer training examples overall, but just something we have to deal with. The remaining missing values are in the furnishing column, which is a categorical feature. The parking column, which is a count feature. This actually indicates the number of parking spaces that the house has. And the type column, which is also a categorical feature. Now, depending on what types of categorical features these are, we're going to have to impute the values differently, maybe. So, for the categoricals, we can get a little more information by getting a dictionary that maps a column name to the length of unique values in the column. So I'll take x subcolumn dot unique and then take the length of that, and I'll do this for every column in x.columns. So we can see how many unique values we have in every column, but I want to limit this down to just the categorical columns, or the text columns. So I can say x.select dtypes and specify a data type I'd like to select, which will be object, and then get the columns for those. So these are just the object columns. And I can now see what kinds of, how many values we have in each. And I notice we have one with 300, so this is definitely going to be one-hot encoded. The other ones, I want to check, okay, so we have missing values in furnishing and type. So these three, this 3 will become a 2, and this furnishing will become a 3, because one of those is a missing value. We can actually see a full list with list instead of length. But I don't want to see locality because it has so many, so I'll go and drop locality over here. And now we can see how the actual values inside furnishing, the actual values inside status, and transaction and type. And so it looks like all 3 of these are binary features. That means they only have 2 values. I'm not counting the missing value here, so if we don't count that, this also has 2 values. And binary features are quite easy to encode. You just pick one feature, one unique value, send it to 0, take the other value, send it to 1. So in terms of filling in the missing values for type, we will probably want to use mode in this case. Because, well, you can't take the mean of, you certainly can't take the mean of a text of strings. So by picking the most frequent value, it seems to make the most sense. So fill missing values. I'd also like to point out about the parking. This is a count feature, and we could fill it with the mean. It really wouldn't make much difference to the model, but it wouldn't. It doesn't really make logical sense because these are integer values. It's a count feature. So if the mean came out to be 2.75 or something, it wouldn't be like any of the other examples. So I'm also going to use mode to fill in for parking, which will return back the most frequent integer. So for each column in parking and type, these are the two value. We have this one and we have this one. These are both going to be imputed with mode. And we can take the column and call fill NA on it. That will allow us to fill the missing values with whatever value we specify here. And we're going to specify the mode of the column. Now, this actually returns a a pandas series. So if we want to get the actual value for the mode, we have to subscript with 0. And then I want to store that back into the original column, like so. Alright, so if I run this, and we check over here, we should no longer have missing values. The only one we have it in is furnishing. And for furnishing, the reason I didn't fill it with the mode, we could maybe if we wanted, but we have more than 2 values in this column, 3 values actually. And this, if you wanted, you sort of could consider this as an ordinal feature, because technically you could say there's an ordering between these values. You could say that unfurnished comes first, then semi-furnished, then furnished. But the problem with ordinal encoding this is we don't really know we don't know how furnished is semi-furnished. Like if we did 0, 1, 2 like that, the spacing of that is sort of arbitrary. So I think we'll one-hot encode this. And the reason I didn't fill the missing values is because when we're doing one-hot encoding, it'll take care of the missing values for us. I'll show you that here. If we use the getDummies function from pandas, we pass in the furnishing column. Each unique value gets its own new column, and if there is a missing value in here, we just get all zeros across. So a 1 represents the original value of an example, and if there was a missing value, it'll just be all zeros. So we don't have to actually fill the values with anything. Now let's actually do the one-hot encoding. Well, we'll do the binary encoding and then the one-hot encoding, but I'm just going to create this function that can do it for us. So for the one-hot encode function, we're going to specify a data frame and a column we'd like to encode. We're going to make a copy of the data frame, and then we're going to get these dummy values, dummy columns. We'll store it in dummies, and we use the pandas.getDummies function. And we're going to do that for whatever column we pass in, and specify a prefix. Now down here, if I specify a prefix here, let's say I make it the same as the column name, then it just adds that prefix to the beginning of each column. And this way we know where each of these dummy columns is originally coming from. So up here, I'm going to make the prefix the same as the column name, and then we're going to take those dummy columns and concatenate them onto the end of our data frame. So df equals pandas.concat df and dummies, and I'm concatenating along axis 1, so side by side. And then when we're done, we can drop the original column from which we created the dummies, since we no longer need it, and return df. Okay, so that's our one-hot encode function. And now we'll do the encoding. I'll do the binary encoding first, since it's simpler. Okay, there's 3 binary columns, these ones: status, transaction, and type. So let's do status first. So all we have to do to binary encode is call the replace function and specify a mapping for the unique values. So if we look down here, status has 2 values, ready to move and almost ready. So why don't we map almost ready to 0, and we'll map ready to move to 1. And this will perform it for us. All we have to do after that is store it back into the column. And we can do, I'll indent them so it's easier to see. And we can do the same thing for the other 2 binary columns. So then we had transaction. And the two values in here are new property and resale. So why don't we say new property can be 0 and resale can be 1. Alright, that's done. And then we have type. Type has apartment and builder floor. Whoops. So we can maybe we'll make builder floor 0 and apartment 1. Alright, if we return this now, you can see that status, transaction, and type are now encoded as 1s and 0s instead of as strings. And we're almost done. Now just the one-hot encoding. So these 2 we need to one-hot encode. So I'm going to do them each separately. I'll show you why. We just call the one-hot encode function we created earlier, passing in a data frame and a column. So we pass in df, and our column here is going to be furnishing. And then we'll do the same thing for locality. Now, I'll return this, and you see the column names got all messed up. And that's because at the end here, we had a unique value in the locality column that's really long. And so when we have sort of like unprocessed values in a categorical column, but it's still a good candidate for one-hot encoding, we might want to consider renaming the names of the columns. Now we will lose some interpretability. We'll lose knowing which columns, which areas these actually were. But I think it's worth it, especially because when I train the models later, there actually is a problem. I think it's with LightGBM. It doesn't allow for strange column names, and there's like some characters that it doesn't like in there. So I'm going to go and I'm going to rename the columns before we create the dummies. So in our one-hot encode function, I'm going to include a flag argument parameter called rename. It'll be false by default, but if rename is true, so if we specify it to be true, then we're going to take the column and call replace on it, and we're going to replace like how we replaced before with the mapping. We're going to map for every x in the column. We're going to map x to I, and these are defined here for every I and x in enumeration of the unique values. So if we take the unique values and enumerate them, that means we get an index for each one. We can then create a mapping that maps every element to its own index. And that way we just change the text names to numbers. And let's run this. And then down here I'm going to say rename. First we'll have false for furnishing because we don't want to rename it, but for locality we do. So now it didn't seem to work. Let's see what's wrong. Oh, I didn't actually store it into df subcolumn. Alright, there we go. Alright, and here we go. You see we now have the normal column names again, but the localities have been given numbers instead of those long strings. Okay, and I think we're ready. There are no more missing values if we check. Missing values are all gone. We can verify this by summing down across the series. No more missing values. In addition, we should no longer have any object columns. We can check this here. Oh yeah, I have to drop this off the end. No more object columns. And that means we're ready to split and scale. So let's split the data frame into x and y. Y is going to be the column we're trying to predict. So we can get that from, I think it was per square foot. And then x is all the rest of the data. That's our feature data we're going to use to try to predict the target. So we drop it from axis 1 and store that into x. Then we do our train test split, and this will create 4 new sets of the data. So we have x train, x test, y train, and y test. And that we can get with train test split. We pass in x and y, and we specify a train size. We can say 70%. Include shuffle equals true, which is on by default, but good to see that this function actually shuffles the data before it makes the split. And because there's a shuffle, we want to include a random state to ensure that the split is always made in the same way when we try to reproduce the results of this notebook. Alright, and after train test split, we can do the scaling. So let me return this first. So we'll actually return these 4 values and then get them back over here. And we take a look at x train. So this is just 70% of the original data, and it no longer has the target column in it. If we look at the mean of every column, they're all over the place. We have some with very high mean, others with a much smaller mean. And if we look at the variances, they're also all over the place. Some of them are extremely high. You know, I just realized something. We do have this price feature in here. And so I'm wondering if it'd be better to try to predict the price feature. If we look back at this, at the end, this is price per square feet, or per square foot. And this is the total price in rupees. Now, I wonder if it'd be better to just predict price, because, well, we definitely can't leave them both in. One of them is telling about the other. However, this one, this one has a, we might be able to calculate the actual, oh no, we have the area, right? Area is in here. Okay, we have square feet, and we have these price per square foot. And because there are missing values in this column, I actually want to drop it. I didn't notice this before. I should have been paying more attention. But per square foot, we should drop this column and just try to predict the price. So I'm going to go up here and just modify our function. That's a nice thing about having a function like this. If you notice you want to change something, you don't have to go back and find where you changed it. You can just remove the part that you don't want. So instead of dropping the rows with missing target values, we're just going to drop the price per square foot value. Actually it's just per square foot column. So we'll remove this, and then it just becomes df equals df.drop per square foot axis 1. And we just have to go through, if we ever mentioned it, change this to price. So the new label is going to be our price. And we knew there were no missing values in the price column. So if we return this now, just want to double check that we don't have any missing values. xtrain.isNA .sum. We have a missing value. Okay, so we have to take a step back, and let's actually return df. So that's before the split is made. We're just returning this, and we'll store that back in x. Take a look at x and figure out what's going on here. So where are the missing values? In bathroom. That's very odd. Isn't that odd? There was no missing value there before. Oh, you're right. It's because the missing value was actually located in one of these missing rows. So we had dropped those rows, and one of those had contained the missing value for bathroom. And this is number of bathrooms, which is also a count feature. So a lot like parking, we're going to fill it with the mode. So all we have to do is up here, just add in bathroom. Yeah. Okay. Bathroom, like that. And if we run this now and take a look, we count up all the missing values again, sum over both axes. Wait, there's still one. So let's see where it is. Wait, did I not do this correctly? Oh, I'm doing on an x train. Sorry, it should just be x. Okay, so I think we got rid of it. There we go. No more missing values. We also shouldn't have any object columns. I'm not even going to bother. We know we don't. Everything's numeric. No missing values. We're ready to go on to scaling. So let's bring back this split here. This time we are splitting into price and the rest of the data. And down here, actually we want to return these 4 values. And then get back xtrain. And like I was saying, the means and variances of these columns are all over the place, and that can confuse a lot of models, and it can you can get much worse performing models than if you standardize the columns. So we're going to scale with a standard scaler. So I imported the standard scaler from sklearn, and what that does is it just gives each column a mean of 0 and a variance of 1. And we want to fit the scaler just to the train set. We don't want to fit this to the test set, because we sort of want to pretend that the test set has not been seen yet. So we can then transform the train and test set using scalar.transform and store that back in xtrain. But this actually returns a numpy array. So if we look at this, it's scaled, but it doesn't look nice. We want to turn it back into a data frame after with pandas.dataframe. And I want to keep the indices the same as they were before. So index equals xtrain.index. And then we'll keep the column names the same as they were before. So columns equals xtrain.columns. And I'll do exactly the same thing for xtest. Just change these to xtest here. And we're good to go. Alright, we have it back, but if we look at the mean of each column, they're all really close to 0. And the variances are all really close to 1. That's 0 because it's a problem with the one-hot encoding, because it creates only one value. Maybe if there was only one instance of that, it could have ended up in the test set or in the train set, in which case there's only one value, which maybe there's all zeros in the train set, so the variance is 0. You don't have to worry about that. It's really not such a big deal. There are ways to deal with it if you want to, though. So I think we're ready. Yeah, we're ready. So let's look at a Y train just to be sure. This is all the prices. These have not been scaled, and the indices between them match up. So now let's start training. So we're going to use a whole bunch of different models today, and I will bring in a dictionary that maps the model name to the instance of the model. And this just allows us to train all the models in a loop. So for name and model, in models.items, .items will return the key value pairs of a dictionary as tuples. So then we can say model.fit on the train set, xtrain, ytrain, and we'll print out a little confirmation message that says that the model was trained. Alright, and while that's training, we can start displaying the results. And to display the results, once they're all fit, is quite simple. We can again iterate through for name and model. For name and model in models.items, we'll print out a message that says the R² score that the model gives on the test set. So R² score is a great way to measure the performance of a regression model. And it's basically a measure of how dispersed the data is around your fit. So we can say the name of the model followed by R² score. And then we'll display the R² score to, let's say, 5 decimal places. And format that with model.score, which is how we get it. We just have to evaluate it on the test set, and we'll get back the R² score for every model in our dictionary. Alright, and here are the results. Alright, so not too bad. We have some models that are doing not too well, especially the simple linear regression is just completely failing to find a fit. This is the highest value an R² score can have is 1, but it can go deep. It's not lower bounded, so it can go really deep into the negatives like this. This is just terrible fit. These ones also not doing so great. They're much closer to 0 than this, but still they're not really finding it. However, all the rest of the models are doing a decent job. K nearest neighbors comes next with a 0.59. Then we have our linear regressions. These are with regularization. So L2 or ridge regularization is with the squares of the weight of the weight values, and then the L1 regularization is using the absolute value of the weights. So trying to minimize those. And these are both pretty much the same. Not quite as good as our other models, though. We have a decision tree with a 0.69, and then all the ensemble models are really taking the cake here. Light GBM with the lowest score of 0.77. Then we have gradient boosting. No, then it's random forest, then gradient boosting. Cat boost after that, and finally the winner, XGBoost, with a 0.875 R². Alright, so that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.